So yes, I am now in Pisa, but this work has been mainly done in Aalto University in Finland, and the main actor of this talk is going to be the bound states in the continuum. So what are bound states in the continuum? Abbreviated with BIC, and I will here discuss symmetry-protected bound states in the continuum. So those are, when you think of a bound state, you think of a localized state. You think of having, let's say, some sort of confining potential, and this confining potential will pin your wave function in some position, and that position is bound. But then you can have also like a continuum of modes that are freely propagating. Think of light that goes into air and space. You can have some modes that are leaky resonances, let's say. So you have a propagation, but this propagation sometimes it's pinned up, and you can have this very special states which are bound states in this continuum of modes. So they have the same energy as the continuum, but for some reasons they are appear to be localized as they were bound by some potential. So these solutions are typically found as a general wave phenomena. So they're found from quantum mechanics, acoustic systems, and of course for the purpose of this conference, in photonic systems. And in photonics, one way to see them is to think of what is happening in a photonic crystal. So a photonic crystal is a piece of material where you have some modulation, spatial modulation of your refractive index. And those are basically, you can see them here. So you have some slab, and then you could have some modes which have the linear dispersion of your photon living on this system, and then those states are naturally trapped in your crystal. So in the same way as electrons are trapped into a solid state crystal. Then of course you can have like a gap, because those states, since the refractive index is acting as a potential, you have energy gaps, like band gaps in solid states. And then you have another region here, this called radiation, where you have some states that exist in your crystal, but then those states can also escape away from the crystal and go into the continuum. So this is actually the reason why many photonic crystals are observable, because you pick up this light in the radiation. And so you have these bands here is in radiation, but then you can have some states, and those states are typically appear protected by symmetry, meaning that there is some symmetry mismatch between a state that is going to be your bound states in the continuum and the rest of your band. So they're also interesting states because they happen to have a topological origin. The topological origin comes from the fact that they can be seen as light polarization vortices. So we are talking about light, so we have to remind that light has a vectorial nature, as opposed to just a simple scalar nature of quantum mechanics wave function. And therefore, you can imagine that in your momentum space, if you track what it's the polarization vector doing in this space, you can have some points where the polarization can not be defined just because you can track them some winding. And then horizontal and vertical polarization meet at some point. And then at that point, you cannot define in a unique way the polarization, and therefore your intensity of the field has to go to zero. So from mathematical and topological perspective, you can define what is called the winding number. Basically, you're just counting how many times your vector winds in your space around the singularity. And so you can have positive or negative windings, also multiple order of windings. So these are states that are we have seen in the first talk by Sonia, and the main difference here is that instead of producing them with some spatial Laguerre-Gauss beams and so on, we're going to produce them by symmetry, and the symmetry in case is the rotational symmetry that we are going to implement in our lattice. So in order to convert like the terminology from mathematics into more physical intuition, I need to introduce you what group theory and irreducible representation is. Okay, don't be scared. It's just modes, like normal modes, of oscillations, let's say, in a system which is rotationally symmetric. So imagine that you have, in this case, a C6 symmetry, meaning that you have, let's say, an hexagon, and then this hexagon is invariant by rotation under 2 pi over 3. Then if you think of what are the normal modes, you always have a mode, let's say, that it's oscillating everything in phase radially. This is also called a breathing mode. You can have a mode that it's where the phases are, let's say, all pi differences, and so it's a sort of shear mode, very weird mode. Then you can have all modes that are, or particles that are, let's say, oscillating all in phase, and another type of weird mode. So these two modes are actually, they are part of a doublet, so you have an accompanied mode associated with them. But for simplicity, let's just consider these 4 modes, and they are typically represented with this terminology. But the crucial thing is that you need to understand how these modes behave when we apply the rotational symmetry. So when we rotate them, you see that one mode picks up 0 phase, the other mode, all the arrows are basically swapped, so you pick up a pi phase, then here you pick up a pi over 3 and a 2 pi over 3 phase. So already from here, if you are quite imaginative, you can say, yeah, I can kind of see that there's something winding around already here. Here, maybe, yes. Here, definitely nothing. It's boring. Here, probably. So I guide your eye, and over here you could see that you can convince yourself that if you calculate again the winding number that I have introduced in the previous slide, you can see that you have a vortex with a +1 charge, -2, 0, and -1. So in principle, by knowing what is the argument of this irreducible representation, so knowing how your eigenmode will rotate, will pick up a phase on the rotation, you can introduce and you can calculate immediately what is the topological charge that you expect. So these are all modes that will appear at let's say, gamma point emission of your lattice, meaning that if you're looking at the lattice, you're looking at vertical emission, and then these are all the type of modes that you can see. So they are particularly interesting because, of course, they can carry on optical angular momentum, so they can, of course, be used. If you can generate manifold of them, then you can use for multiplexing and carry signals, independent signals from each other. And also, since these bounces in the continuum, they're also very nicely decoupled from all other modes, it means that they are very good for trapping light. And so a good way to exploit them is to make a laser out of them, because for a laser, basically, you just need to have a gain medium, you need to have your trap state, and then in principle, you can use these states which have a very large quality factor to trap light. So this is what actually has been done in a very series of papers. This is very limited references, and also one other additional thing is that they can be used also into addition with light matter interaction, forming polarity on BEC. And in the group of Daniele Sanvitto, they have been able to condensate in one of these BIC modes, and they've actually seen that they offer a sharper and smaller threshold for condensation compared to other modes. So they're useful, and we've been realizing these modes in plasmonic setups in the group of Päivi Turma in Aalto University. So plasmonic setups is basically an array of metallic nanoparticles. So imagine this metallic nanoparticle, you illuminate them with light, and then what happens? The electrons gas in your metal will go up and down because it's invested by this oscillating electromagnetic field. Then you drive your plasma oscillation. So essentially, they behave like antennas, so dipoles. So you have all your nanoparticles, and you can associate a dipole emitted from each of them, and you'll have like the radiation that's going into the in-plane momenta. You can go to the lab, and then by coupling from the outside, you can observe what are the dispersion of these modes. One nice observation is that typically these metallic nanoparticles are very nice for confining the electromagnetic fields closer to the particles, so in some form of hotspots, meaning that can really go to the nanoscale and enhance a lot the light-matter interaction. Then the system that was realized, it was triangular lattice, where each unit cell is actually composed by 6 particles. So remember the symmetry that I showed you before. And what was done is that the size of these hexamers, let's say, was varied from a minimum of 50 nanometers within each other to a maximum of 200 nanometers. So we have, let's say, 4 types of classes of arrays. And what happened is that by putting this nanoparticles array into a gain medium, which is dye molecules, and were brought to the lasing regime, different lasing thresholds and different lasing modes were observed into the system. So it means that something is happening as we change the structural parameter of our lattice. So what is happening is basically, so yeah, these are the polarization resolved measurement. And if you remember again the talk by Sonia, you can immediately see that by looking at the emitted field in polarization resolved, horizontal, diagonal, and so on, you could recognize that these are vortices because you can see a polarization winding around. So we identify those as really the families of polarization vortices. And what is happening is that theoretically we calculated what would be the quality factor of the mode, meaning the real part of the energy over the imaginary part of the energy. And we saw essentially that the mode that was lasing in these 4 different families was always the one with the highest quality factor, meaning that as soon as there was a switch, let's say, or a transition between one mode quality factor with another, as we varied our parameter that changed and increased the hexamers, we were seeing a different mode lasing. So we realized that this is more loss-induced than energy-induced. And the reason can be also found by analyzing really what is spatially the modes, what these modes are doing spatially. So these are the sets of the all 6 modes that exist in the system for the 2 different parameters. In this case, the lasing mode was the B prime, and in this other set of case, the lasing mode was the A prime. So you can see that between these 2, the symmetry, spatial symmetry here is the intensity of the electric field in plane, is not changing so much. What is changing is really the position of the nanoparticles. And then you can see that essentially the mode that is always lasing is the one that has the nanoparticle the furthest away possible from this high intensity electric field, meaning that the electric field was able to couple very well with our gain and then have the maximum overlap and the maximum quality factor for lasing. So while over here you see the B mode is mainly damped by the presence of the nanoparticle. So this actually gave us the intuition that it's possible to design any type of mode in principle, because we know that there is a relationship between the charge, the topological charge, with the symmetry and the rotational symmetry. So in principle, by going to higher rotational symmetry, by increasing this n, you can have higher charges. And then we have a way to design how to make the largest topological charge to lace by increasing its quality factor. So basically what we did is that we fixed what is the rotational symmetry. In this case, it would be C12. So we'll have a quasi-crystal, not a crystal anymore. And then by group theory, we know that we need to implement a mode that is composition of plane waves with a certain phase factor, which is going to be the one represented by the mode that we want. And then look at the field and then place the nanoparticle the furthest away possible from the high intensity field. This was done. This is the SEM image of the crystal that was realized. So you can see that there is really no translational symmetry anymore, but only rotational. And then when analyzing the emission in momentum space, this was the pattern that we observed. So it might look chaotic at first, but maybe you can kind of see that there is some sort of highly ordered structure, which then it's really 12-fold rotational symmetry. I know the laser is very nice in match with the color. So by looking at the central area where over here, which is the one where the intensity is coming the most closer to the this gamma point where we expect these topological charges, we see that it's actually like a hierarchy of charges, because when we look at the phases, here the color code is such that a black circle is a -1 charge and a white dot is a +1 charge. So you can see also over here as a function of going away, so moving away from the gamma point radially, we start with a charge of -5 here at the center and then jump to a +7 because you have all these charges that are emerging due to the quasi-crystalline symmetry, and then higher to -17 and even -19. So we can really have whatever vortices and actually hurricanes, we would say, of light. The system was lasing, and it was lasing coherently. So you see two snapshots before threshold and after threshold, done with some interferometry, just to show that it was the entire sample. Even if it's a quasi-crystal, it's not something randomly local, but it's really a property of the entire sample that was lasing. And this is like a cross-cut momentum versus energy to see that it was very spread, as you saw also in the previous slide. It was very spread over a wide range of momenta, so it's a sort of quasi-flat band-like feature. So in the few minutes that will remain, I want now to connect the topology of these bounces that we have seen as light polarization vortices to the global topology of a band. And in order to do that, I want to be more practical and more rigorous in determining what is now the Hamiltonian of the system, because so far we are relied on rotational symmetries of modes at a particular momenta. So if you think of how to define an effective Hamiltonian for this photonic crystal, I told you that basically you need to have some spatial modulation of your refractive index. So if you have, let's say, a uniform pattern, then you will just have two counterpropagative modes that are transversing. So this is like the energy dispersion of your light. And then as soon as you have your patterning, then this is able to open a certain gap. But then you can also imagine, since this is a model that it's coupled to the continuum, so you have these radiation losses, then you can introduce radiation. But then the radiation is done in a way that you could lose some light from a counterpropagating mode, go to the continuum, but then recouple and somehow recouple to the counterpropagating mode. So in the end, you will have a sort of non-emission radiative coupling, and then this will create, so you have the losses uncoupled for the two modes, and then when you couple through the wave pattern guiding, you will have that the imaginary part of your modes will also acquire some dispersion. And then you will see that on these two bands, one mode gets zero losses, the other mode gets all the losses. And then we identify the zero losses mode as the BIC. So how to generalize this in 2D? It's also very, very simple. You think instead of now the two counter-propagating modes, which are Dirac cones in 1D, you think of 2D Dirac cones, okay? And those are, depending on your geometry, let's say if we are now in the square geometry, you need to consider these light cones that are originating from the reciprocal lattice vectors in your momentum space. So the energy dispersion is going to be meeting where these cones are meeting. So you will have like a Hermitian part where you have the energy dispersion of the modes, and then those modes are coupled in a way that we are now doing a sort of tight binding, but now in momentum space, not anymore in real space. But regarding this non-Hermitian coupling, then you would need to look at what's happening really close to where these modes are meeting and look at the polarization of the light, because only waves that are copolarized can interfere and can give rise to this mechanism of coupling. The other ones would not. So the dispersive, like the non-Hermitian Hamiltonian, would look like that. So this is the total Hamiltonian that we are studying, and it's approximation that is valid near the gamma point of the square array. So by again, by studying what are the energies of the modes, we have the real part and the imaginary part, and again you see that you will have this linear dispersion, this bands over there, and then from the imaginary part now you see that we have two modes that are now with zero imaginary parts. So we have now two bounces in the continuum, and those bounces in the continuum, they have different topological charges. We can see that by reconstructing what would be the electric field in the system by taking the polarization vectors now, keeping in mind that the polarization vector needs to be orthogonal to my momentum defined in this basis. And then if we plot what is the polarization ellipse in this in the vicinity of these modes, then you have a BSE winding +1 and -1 in these two states over there. So yes, we have defined the Hamiltonian finally. So I'm very happy as a theoretician because now I can define topological quantities and I can define the Berry curvature. So we realized that the Berry curvature of this system is only non-zero when we have non-Hermitian origin, so when we have that the losses are actually treated to zero. So what we did is that we have our non-Hermitian Hamiltonian. We can diagonalize the Hamiltonian from the left and from the right and construct this quantity, which is known as the quantum geometric tensor. And the imaginary part of this tensor is the Berry curvature. So define it in this way. But typically in photonics, in this seminal work by Olivier Bleu, Sokolzhnikov, and Malpwesh, they defined the Berry curvature from the emitted light in the radiation. So they looked at the polarization vectors and the Stokes vector, so meaning that you remap your electric field on the block vector, on the block sphere, sorry, and then you define the angles of the polarization, and the Berry curvature has this formula. So, okay, it seems that you have two ways of calculating it. By the way, the Berry curvature in general, the quantum geometric tensor with this method were realized into the setup in the Tormas group, exactly by doing what I just explained. So they looked at the dispersion and then they did differential measurements of the intensity between the different polarization, a sort of dichroism for the linear and the circular polarization, and reconstructed these objects. And they found that the Berry curvature, in particular, is mainly localized on the diagonal of the Brillouin zone, and this is similar to like the same results that we found as well. So this is the representation. Now we have the four bands. This is the dispersion across the cut from X gamma to M, and then this is the imaginary part. Again, the BSE modes are on these lower two bands, and here is the band 1, band 2, band 3, band 4. We have the polarization polarization vortex. So you can clearly see here the winding of the polarization, while here there is nothing winding. So these are the two trivial bands, and then this is the these are the bulk calculated Berry curvatures and the radiation calculated Berry curvature. And you can see that for the case of the bands where there is no BIC, these two quantities are almost comparable. But for the case where the BIC is found, these two quantities are not comparable at all. And we actually predicted a sort of breakdown of this correspondence between the bulk and the radiated calculated quantities. So by scanning, let's say, the parameters of a lattice, we can identify regions where this quantity, which is let's say, the discrepancy of the bulk minus the radiated, will be maximal. And we also calculated where the transition, let's say, where the bounces in the continuum and these polarization vortices are located. We plotted on top, and we found exactly a nice overlap. So it really seems that the discrepancy is maximal when this polarization vortices do exist. So with this, I come to my conclusion. We have seen these classes of states as polarization vortices in the far field having a topological origin. We have seen that we can lace in those systems, and we can choose with arbitrary will what it will be the charge dislacing. We can see that these can be manifested into the far field topology, and we actually came out with like a breakdown of the correspondence between bulk calculated and radiation calculated topology. And with that, I thank you for your attention.
Okay, Grazia, thank you so much for enlightening presentation. Do we have any questions from the audience? Okay. Aha, Sonia has.
I really enjoyed your talk. I like the characterization in terms of symmetries, which we haven't thought of in that much detail. I need to read more about that. Okay. But my question is, you looked at the rotational symmetry only at the moment, but of course, yeah, there should also be something in the radial direction, which will be a lot more horrible with hyperbolic contributions. Did you look into that at all?
You mean the radial direction of...
Yeah, like something like a radial symmetry quantum number?
Not sure I understand what you mean. Because we looked at the rotational symmetry of the lattices, okay?
No, I mean of the symmetry itself at an individual location.
In real space.
In real space.
Okay, so you mean that the unit cell itself can have a different mismatch of between the
okay. Not if you only have the 6. Okay, maybe I need to. Maybe I ask you afterwards.
Maybe we discuss over coffee break.
In more detail, but I feel there's another part of the symmetry that there must be something more.
I mean, it could be. So we restricted ourselves with symmetries that are matching. Of course, if I kind of understand, but not sure, you could have a mismatch between the symmetry of the lattice and the symmetry of the unit cell. Then in that case, you will need to calculate what is the overarching symmetry.
Yeah.
And we didn't do that in this work, but it's something that, of course, you need to think about it. But we can discuss later.
In more detail. Thank you.
Sorry. Additional question from the audience?
Thank you very much. I just had a question because you say like the mode that has the highest quality factors then wins, and then you will lace on this mode like it was the start. But I think I quite saw it for 3 modes, and then the 4th mode appear.
Yeah.
But it's to me there's still one mode that has a higher quality factor.
There was a 4th mode that was not very much correct. I agree. This one.
The blue one.
This one. Yes. I am sorry I don't have the data for this one. But what happened over there is that we had a multi-mode lasing. So essentially, I don't know if it's already visible over here. Yeah, because it's this one. It first starts lasing, then it goes down, and then it goes up again. So it seems that there is a mode that is starting, and then something else will win. And a sort of naive interpretation, yeah, it's in these two modes. You see, these two modes have the almost complementary overlap of the gain with the symmetry of the mode, meaning that they are competing for different spatial gain. So you can have one that wins and then the other eventually wins. Okay, so what we found is that, so from the theoretical calculation, there is clearly only one that wins, but then this one for this weird gain competition was winning in the experiment. So, but this is a special mode.
Okay.
I can show you the latest data.
That's fine.
Yeah.
Okay, any more questions? Grazia, how do you think, what are the highest topological charts that can be experimentally realized?
I mean, that's a tough question. Thank you. Of course, there is a threshold between going into higher rotational symmetry and going to the continuum. In the sense, how can you describe a C100 over being just rotationally continuous? But one nice way out that we saw in this paper is that we'll have some arbitrary, so because of windings, okay, you can have some additional arbitrary definition in terms of the topological charge you can get, which is what we saw over here, yes, because expected it was only -5, but we saw in modulus 12 all other charges. So in principle, don't let me say a number, but we can go high, I think. Probably not to hundreds, not to thousands, but 50s maybe? I don't know. I don't want to say.
Okay, any more questions? So let's thank to the speaker once again.